Welcome everybody on Zoom, welcome everybody in the lecture hall, welcome everybody from the future. Those who are been watching us, this is the grand final of the course. So today we are going to celebrate everything that we have learned during the semester. I'll give you an overview. Again, show you that everything we've been doing are just small pieces of a big puzzle that all make sense together. And then we'll proceed with the exam information, any questions you might have about the exam, and then we'll have a quiz, a big quiz, a bit like Ijskage 100, where you will have a chance to play against the TA team if they are courageous enough to wake up early and to play against you. What have we learned during this this semester? On the very, very high level, the most important lesson to manipulate data, to query data, is to understand that data has shapes, just like matter has shapes. Shapes decide all the rest. When you have a shape, then you can decide on a data model, then you can decide on a query language, syntax, and so on, and on the system you want to use. Why are shapes so important? Because if you make the mistakes of not getting it right, and a lot of people do not get it right, then you are going to end up with something that is slow, because you're not using a system that is optimized for the kind of data that you're querying. So you are going to lose time because the system is going to be slow. But you're also going to lose time trying to write the queries and make it work. So it's both a problem with productivity and with performance. So this is why when you have in the future, maybe a semester's thesis or a master's thesis or a project, or even during your PhD thesis, if you have data, you always need to ask yourself, is it tabular? Is it really something that easily fits in a flat table with rows and columns? Or is it something that is denormalized, that looks more like trees, where you have a lot of nestedness in there? So is it more like a huge collection of stuff that is nested? Is there some heterogeneity, meaning that the same key or feed might have different types in the data? So it's a huge mess. That's an indicator that you might need to work with trees, with collections of trees. Then there are kinds of data we did not cover in that lecture, but it's good to be aware that that exists. For example, there's data that looks like graphs. Graphs is a bit the same as trees, except that you can have cycles. So as you can imagine, it doesn't work anymore to just store it as JSON or XML, because in JSON or XML, you can go down, but you don't have cycles, right? So there are also graph databases that deal with cycles. Imagine like what has cycles, the public transportation network of Zurich, and so on and so on. So there's graphs, then there are also cubes. So the cubes, for some of you who took information systems for engineers, you already know about them. This is very popular in business analytics. If you haven't, then you can take information systems for engineers next semester. And the cubes are even more structured than tables, right? So it's every piece of data, every value has dimensions. For example, the number of laptops that were sold in that year from that person in that country and so on. This is all organized as a cube. And finally, there is a fifth kind of shape that is just text. It actually gained in popularity in two ways. First, 20, 30 years ago with the first search engines over the internet, where we massively started scaling, indexing the web, and being able to type a few words and retrieve web pages, because web pages is data as text. And last year, with generative AI and these chatbots that can just speak with you, this is all also about unstructured data, so in the form of text. So this is the fifth one. So we have 5 shapes. I honestly do not know if there's any more shapes than this. It might be this is it, these are the 5. It might be that in 10 or 20 years, somebody discovers that there is a 6th shape or there are other kinds of shapes. But whenever you think you have a new shape, really ask yourself, is it just not really one of the existing ones, right? So that's it. These are the 5 shapes of data. And I hope that at least for tables and trees, I could give you a good intuition of what data feels like when it is organized in tables or in trees. One of the benefits of having selected a data shape and having come up with a data model. For example, what is a data model for tables? Well, it says that a table is a collection of rows. Every row associates a column name with some value, and it's atomic, and all the rows have the same columns and so on. That's a data model for a table, right? It's called the relational model. For trees, we saw that typically it's a model with sequences of items, sequences of whatever, and these items can be either atomics or objects or arrays, and then you can nest objects and arrays within each other, right? That's a data model for trees. The benefit you get out of this is typically that you get something simple. You get something simple to understand. You fit your data in there. You can learn a query language. If you did it right, then writing queries should be relatively straightforward. If you start writing queries that have 100 lines of codes, then it might start indicating that you're not working on the right model. All right, so to give you this intuition, right? And there is this quote that the most famous alumni of ETH gave us: everything should be made as simple as possible, but not simpler. And this is in essence what has been happening with big data, is that all of these systems that have been built in the previous 2 decades, which is kind of the big data era, has been built in a modular fashion. Right? Just like in a house, you have the plumbing, the electricity, the walls, and so on. So it's all orthogonal, and you build a big system. So this is divide and conquer. So we looked into this stack of things that we need to build a data management system, and we have it for tables, we have it for trees, and so on. It also exists for graphs and for cubes. Right? So for every data shape, we have a paradigm, which is the big picture of the data shape. We have, I should even have put an S here, data models, because you can have several data models for the same data shape. For example, in trees, you have the JSON data model, you have the XML data model. These are both trees, but they are not exactly the same, right? So data models, syntaxes, query languages, not the same depending on the shape, an architecture on how you actually implement this. Can be on top of a single machine, a laptop, but it can also be on top of a data center with thousands of machines. And now you know how this is done because we've studied it during this semester. And I also mentioned today something that I haven't talked about before, which is the mapping to other shapes, because it turns out that if you have a shape, you can still implement another shape on top of the first one. It's a lot of work, but if you do it well, you can actually achieve a few things. So to illustrate this, so all this, the fact that each data shape has all of this, I'm going to give you a few examples across these 5 shapes. So for example, I put the same 5 shapes here. So on the left, that's the paradigm, right? The paradigm can be everything is a cube, or everything is a table, or everything is a tree, or everything is a graph, or everything is a bunch of text, right? These are the 5 paradigms. And then on the right, there is the algebra that comes with the models. So for example, if you have a cube, you can slice, dice, aggregate, roll up, pivot, cross-tabulate, and so on. Of course, we did not cover it in this semester, so you don't have to be worried if you don't understand what it means. But again, if you were here last semester, then that will make sense to you. Tables, that you know, that we studied, right? So in a table, you can select rows, you can project on some columns, you can rename some columns, you can group, you can aggregate, you can join 2 tables, you can sort tables if you assume that there is an order on the rows. You can union 2 tables if they have the same schema, and so on and so on. So this is what you can do with tables. With trees, you can look up, you can navigate, you can normalize trees, denormalize even more, validate, select, project groups, so some of the things you can do with tables too. This also you should be familiar with trees, right? Tables and trees is what we covered. Graphs we didn't cover, but just so you know, we can traverse a graph, we can find patterns in a graph, we can also select nodes in a graph, we can sort nodes or values in a graph. When we have text, we can filter, map, group, aggregate. In fact, we can use MapReduce with text, right? You can also just input lines of text and process lines of text with MapReduce, right? So that you could kind of do too. Now, what about syntaxes? Well, there are also syntaxes for every shapes. In the case of cubes, there's the XBRL syntax, right, which is used in many countries for accounting purposes, for example. But this is not part of the lecture. So again, XBRL, you don't have to worry about. Tables, CSV. You can naturally store a table in the CSV syntax, comma-separated values. If you have trees, there are many of them. You can use XML, JSON, Avro, Parquet, and so on. So you saw that XML and JSON is actually a textual syntax. BSON, Parquet, Avro, protocol buffers, these are all binary versions of the syntax. BSON doesn't need a schema, Parquet needs a schema, Avro needs a schema, protobuf needs a schema, right? And we saw that it's more efficient to have a binary format. Graphs, again, you don't need to worry about that, but I'm just telling you there's also RDF. Who heard of our RDF? Quite popular for ontologists, right? So RDF, there's an XML version. Turtle is another version of a syntax for graphs and so on. Bunch of text, well, it's already syntax, right? So that's already as it is. So you see, we have also syntaxes for the different data shapes, and we also have query languages for the different data shapes, right? For cubes, again, you don't know what that is, but MDX, I think it means multi-dimensional expression. So it's just a query language that is inspired by SQL, except that it works on cubes. For tables, you have SQL, and SQL now you know, probably in all ways possible, because you've had it in the exercises. We rediscovered it with Spark SQL, and you'll have it at the exam, right? So you really need to make sure that you know SQL. It's undisputed for tables. For trees, it's something else. There are plenty of them. They more or less share the same features. Not all of them have all features, but if you learn JSONic, which we did in this lecture, then you can learn any one of the others, and that should be very easy, right? So we covered JSONic. For graphs, there's Sparkle, not to be confused with Spark SQL. Sparkle, Cypher, GraphQL, and so on and so on. GraphQL, I didn't really know where to put, right? Because technically, I could also have put it in trees, because even though it's called GraphQL, it could be used with JSON too. All right. And for a bunch of text, there's not really a language, but you can write your own codes to do this. In fact, a lot of digital humanists who work with texts and papers and publications, they like languages like XQuery, surprisingly, because XQuery is, of course, it's meant for XML like trees, but a lot of publications are actually in the XML format. So XQuery is quite popular for a bunch of text. All right, but the two languages you need to know is SQL and JSONic in here, right? And we'll help you, of course, I'll tell you about the exam, but we will make sure that you can continue to learn them if you haven't already. All right, something else that I hope you now also understand is the difference between two things. It's very important. It's the difference between a functional API and a functional query language. API, what does API mean? Application Programming Interface, right? API is a huge buzzword right now. All of the venture capitalists and investors are rushing for whenever it's about APIs. So it has become a big thing. And an API is more like PySpark, right? If you look at PySpark and you have the RDDs that you manipulate in Python, this is an API. It's a Spark API that allows you to transform the data. There is also on data frames an API. For those of you who don't like Spark SQL and prefer to invoke transformations on data frames directly in Python or in Java, this is also an API, right? So an API means that you're using a host language, Java, Python, and so on, that is usually an imperative language. And in that language, you have a library that allows you to manipulate data. This is an API. As opposed to a functional query language that would be SQL or JSONic, that is a language that isolates you from all the complexity. If you use SQL or JSONic, you don't care about Python, you don't care about Java, you don't care about anything else. You just have one language that manipulates instances of the data model. It's a very fundamental distinction. Many people don't get that. And it's very important to value the difference between a query language and an API. Typically, an end user, so for the purpose of manipulating data in a semester's thesis, master's thesis, and so on, A query language will be more convenient usually. A functional API is more for engineers who want to implement a more complex system on top, like RumbleDB, for example. It exposes JSONic to the user, but RumbleDB is implemented with the Spark API, right? Because this is leveraging the complexity of Spark. All right, so it's very important to understand the difference. And again, above that would be PySpark, or the data frames transformation API. At the bottom, that would be SQL, Spark SQL, JSONic. Who gets the difference? Okay. Now, something else that we saw throughout the semester is that we store a lot more data today than we did before. The problem is that we cannot read it fast enough because the progress we made at reading the data hasn't been as great as the quantity we store. And the latency, meaning the time it takes to start reading the data, that's even worse. And that put a few constraints on the historical development of big data. The fact that we cannot read it fast enough forced us to parallelize. And now you know how to parallelize. We saw you can do it across machines in a cluster. You can do it across the cores of your machine. This is when we have the slots in MapReduce and in Spark, right? So we parallelize over the slots, and within each slot, we process data, but this is all done in parallel. And the second constraint we had, the fact that we often need to wait until the data makes it over the network and so on. That's because of the limitation of the speed of light. That forced us to batch process. When did we batch process? Well, we did it, for example, well, in the case of MapReduce and Spark, because we process the data in splits or partitions, right? So in batches, in another way to put that. The other location where we saw batch processing is in the storage in HBase, when we saw this flushing and compacting, right? This is also a way to batch process the data. And again, with MapReduce and Spark for storing intermediate results, this is also done in a batch processing way, right? It's called the LSM trees, right? So log, structured, merge trees is the fancy word. This is what happened in our world because we had this constraint. In a hypothetical parallel world or on a different planet in the universe where they didn't have this problem, that they couldn't read the data fast enough, imagine they could read it faster, have much lower latency, much better latency, well, they wouldn't have needed to parallelize or batch process, right? So again, you need to be aware the only reason we did it that way is because of what happens with the capacity, throughput, and latency. This is what forced us to do it in that way. So we saw that because we need to parallelize, we need these computers in data centers, thousands of them, 10 of 1,000. We also saw there's a limitation because at some point for cooling down and for electricity reasons, we cannot put more than 10,000 or tens of thousands at a time. So we have these nodes. We saw that it's all organized in a centralized architecture very often, that there is the data is on the machines at the bottom, and then there is a node that centralizes everything. We saw that it came with a few problems, that if the machine fails, the one that is at the center, then we need to make sure that not everything is broken. So we saw several ways to do that with Yarn, with secondary name nodes and so on, right? Okay. Then we saw that even though these are two different shapes, trees and tables, that tables are a special case of collections of trees. Tables is the special case where your collection of tree is homogeneous and flat, right? Then you have tables. So trees, in a way, collections of trees generalize tables to the denormalized world, right? So it's a generalization of table that is more flexible, and that's a very important point to understand too. In the future, in your projects, you always need to ask yourself, do I really need trees? Because in 80% of the cases, all you need is tables, right? So always ask yourself, do I really need something else than tables, right? Okay. Then we saw that this is part of parallelizing. We did two things with the blocks or the shards or the partitions or the splits or whatever you call them, the chunks. We shard the data into blocks or chunks or whatever, and we replicate the blocks and chunks and so on, right? So HDFS is the first time we actually did that, but we saw that we kept doing that sort of things pretty much every week, right? Sharding is in order to parallelize stuff and spread it all over the cluster. And replicating is for fault tolerance, meaning that if it breaks or it crashes or we lose data, then that's okay because we have a copy somewhere else, right? So that's the replication. Then we saw that when we have data that are collections of trees, you might not have a schema. For tables, you do have a schema always. You cannot have a table if you don't first define your schema, right, in PostgreSQL. But in collections of trees, in this environment, you might drop your data in a data lake without any schema, just like it is. Can be a huge mess. That's heterogeneity. And what you can do is later decide to validate that data against the schema. You might need to clean it up, and you can use a language like JSONic for that. You clean it up, make it homogeneous, maybe make it flat, and then you can save it as CSV and reopen it in a table system, right? And when you do that, you can use validation. Validation is also useful if you want to store some JSON data set in a more efficient format, like Parquet, right? Because you need a schema for Parquet, so you can clean up and validate your data, then store it in Parquet, right? And then, of course, you can query your data. It doesn't need to be valid. You can also query with JSONic, even if you don't have a schema. It's just going to be a bit slower. And you can also serialize your trees, right? It's called serialization. So basically, when you manipulate your data, it's in the memory of your computer, right? And when you save it to disk, that's called serializing. You serialize your data to the data lake as JSON, XML, Parquet, and so on. All right. When you validate, you have to deal with all of these types. And again, that was at the request of one of you. I think it was a great idea that they asked to have a table like that. By the way, this is a table. You see tables are everywhere. But this here is the correspondence of the types across multiple systems, right? PostgreSQL, Spark SQL, JSON and JSONic, and so on, even Python. What we saw here, and that was the highlight of our week, is it doesn't really matter what system you use, they are pretty much alike, all of them. They might use different words, you know, but again, I said it's like Schweizerdeutsch in Switzerland, right? You change the content, it's different words, but in the end, we all understand each other, right? Okay, and you notice between XML schema and JSONic, JSON, it's the same, exactly the same names. And yeah, that's pretty much. Okay. Then something else you can do, and this I didn't really talk about in this lecture, but it turns out that you can implement a system manipulating trees on top of a system manipulating tables, or the opposite, and so on. So you can actually map shapes to each other. This is very complex. If you don't do it correctly, again, you're going to end up with something very slow. However, there are people who try to do that, especially when you build a new system. If you try to implement it from scratch with C++ and dealing with all the format and so on, that might be too complicated. So this is why when people start building a new system, they prefer to use an existing system and implement it on top, right? So you can map. An example of that is if you have a table, you can easily store it as, I should have said trees with an S, right? A table is a collection of rows, and a row is just a flat tree with no nestedness, right? Who agrees with that, right? So if I give you a relational table, then you can store it in MongoDB, for example, or as a JSON lines very easily. Okay, it turns out that if you have trees, you can also easily store them in a graph database. That's just because graph has cycles and trees do not, so it's a generalization. Graphs can be stored as tables. It's basically just a list of the edges of the graph. Cubes can be stored as tables, and if you visited information systems for engineers, then you also understand what I mean here. It's called the snowflake design. Okay. Now there is this project that you have now in the exercises, and I think you got an extended deadline to solve them. I really strongly encourage you to download it, to play with it, to solve the exercises. This will be at the exam. You will have a Rumble instance on your machine that will run locally. There is a paper. We have the link on the Moodle. I recommend you read it together with a 10-minute presentation of the architecture of Rumble. RumbleDB basically uses pretty much, or let's say a lot of what we've done in the lecture. It implements the JSONic language. It exposes collections of trees. It has validation. It has the query language, JSONic. It is implemented on top of Spark, both RDDs and data frames. It allows you to also manipulate text. if you want, you can read from HDFS, from S3, from Azure Blob Storage. So this is kind of spanning over all the material that we've done. And so there are 20 plus students who contributed to this. And the lesson from here, from this, is that the only thing the final user ever sees using RumbleDB is JSONic manipulating data that you read from a data lake. All the rest is hidden, but to you, it's no longer hidden anymore because you've learned now what there is inside. You know how Spark works, you know Spark SQL, RDDs, and so on, right? But this is kind of the lipstick on top when you have a system that encapsulates everything. All right. Now, what about the future? Your future, of course, there is the exam, right? But in the longer future, you will have projects and hopefully you'll have to manipulate data and use what we have learned in this course, right? So what will you have to do? Well, first, you might need to use another product, right? You might have to be in a research group that uses something different, still uses collections of trees, maybe another language, another syntax, but that's okay because you've learned one syntax for each shape, you've learned a few query languages, you will have no problem learning a new technology, right? A new validation syntax and so on, you will have no problem with that. What you are also able to do now, thanks to what you learned, is choose which product to use. Imagine that you are not forced to use any product in particular, you just have data that is given to you, and you need to figure out what you use. Now you can make an informed decision. Can look at the data. Is it more like a table? Can I use PostgreSQL? Is it more like trees? Maybe I can use MongoDB if I need to look it up fast. Maybe I can drop it in a data lake. I might remember that it's faster if I store it in Parquet because it looks like I can validate it and so on. You can make all these decisions now. And because of what you know, you will gain a lot of time compared to if you didn't have this knowledge, right? Because when you make the right decision, you will be more productive and get more performance. And now some of you, probably the probability is higher with the computer science students, but some of the students of my classes will probably be in a position to actually design whole new products, right? But even to design whole new products, you need to understand the existing ones, right? So this is why it's still useful. But maybe there will be new technologies in 10 or 20 years that will have been designed by some ETH students, right? So again, you have to ask yourself in your future thesis, what's the shape of my data? Take the time to look at your data under all angles and figure out, is it a table, is it a tree, collections of trees, and so on and so on. Is it nested, is it messy? How much data do I need to store? Am I looking just at a megabyte or a gigabyte? That fits on your laptop, no need for a data center, right? Are you looking at terabytes, petabytes of data? Then you might need a data center, right, a cluster. So this is also an important question to ask. This is also something that many people get wrong. A lot of people jump to a data center or to a cluster just because that's the latest cool thing. But if you have a gigabyte of data, it's ridiculous. You are not going to a data center for a gigabyte of data, right? And in many, many cases, when people start companies or create a new startup and so on, they don't need a data center. They actually can start with a prototype on their laptops. For a startup, when you start small, the main benefit of a data center is not really because of the scale. It's more because it's unpredictable. When you create a company, you don't know if your customer base is going to grow. And in a data center, you can just grow and scale by the push of a button in case you have a lot of customers. That's the main reason. But it's not necessarily because of the size of the data. Okay. And then what you want to do with your data. That's also an important thing to decide on the API, query language, and so on. It's very complex. Maybe an API starts making sense, but for simple cases, a query language will bring you farther. Right? And you need to ask yourself, this is the DNA of ETH, at least it's repeated all over the place here, critical thinking. Always ask yourself when you try to design something new, a new language, a new product, and so on, am I not reinventing the wheel? Am I not redesigning something that already exists? You need the wisdom to be able to tell when something already exists and you can just go ahead and use it, right? Okay, and another wisdom, but now I've already told you, always ask yourself, can I achieve the same thing with my laptop? Do I really, really, really need a data center and a cluster of machines? Maybe, but in some cases, you can just do it on your laptop. Your laptop has, it has multiple cores, right? You heard about 4 cores, 8 cores, 16 cores. You can parallelize on your laptop. It's incredibly powerful. You wouldn't believe what your laptop can do in terms of power and parallelization, right? And Spark runs on your laptop, RumbleDB as well. All right. So what does the future have in store from us? Well, it's difficult to predict the future. Maybe 2030 is less risky than at the end of the century. So I try to make predictions. I update them, of course, every year because things are changing. This is kind of my wish here, and that's because I hope that people will have a better understanding of the difference between an API and a query language, but hopefully in the future, technologies like MapReduce and Spark, they will be hidden. That's not what the final users see. The final users, they can use query languages like SQL, JSONic, and so on in order to query the data. And MapReduce and Spark is like what's inside your car or inside your computer, but I don't know if you still do it. When I was a kid, we would build our own computers and assemble everything with the components, right? I don't know if your generation is still doing it. Maybe some of you are still doing that kind of things, but it's harder because now you have laptops and it's so small and that it's more difficult to do these things. But maybe there are some of you who has a desktop computer at home that they assemble themselves, components. You do have people who do that, right? Okay, it's actually kind of cool. But for many people, they need to be isolated from that because it's very complex, right? So this is why you cannot expect everybody to learn Spark and MapReduce and such APIs. But learning a language like SQL, a lot of people, even without computer science background, can learn a language like that. There are a lot of business people who write SQL, right? So this is kind of what it should look like in the end. Doesn't matter what shape you're looking at, but this is the idea. Now, we need standardization. Tables, that's fine. It's achieved. Everybody agrees that SQL is the best way to query a table, undisputed. But we haven't achieved that for all shapes. Because we have a problem. You might know the XKCD, but we have a big problem with the collections of trees. So the problem is that there's a lot of standards already and a lot of different programming languages. And every couple of days or every couple of weeks, there is a company or an engineer that suddenly has an epiphany and realizes, oh, we need a query language for JSON. And so what they do, all the existing languages, they're not good enough. Let's just try to do better than that and unify them, right? And then you end up with yet another fancy new website that says, we have a new language and blah, 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 with all the bells and whistles. But actually what you end up with is just one more, right? And so this is the situation we have today. It's everything but standardized. Some of them are actually technically standard because, for example, XQuery, JSONic, and so on, this was actually a cooperation across many, many different companies in the W3C, the World Wide Web Consortium. But even in spite of that, there is still this proliferation of languages. My hope is one day this will be consolidated and there will be one language that all products use so that it's interoperable, right? So this is what I hope is going to happen, right? Okay, but now, I promise I had it a few years ago too, it's not new this year, but it's just accelerating. It's when I say the final user will not have to worry about the details of MapReduce, Spark, and so on, but instead, we will just talk to the databases. This is the essence of all this progress that we see with generative AI and ChatGPT and the like, right? So we might in the future talk, or most people will actually talk to their database, right? And then it will be translated to SQL or JSONic or whatever language, and then an answer flows back. Now you're probably aware, if you use these systems, that we're not there yet, right? They're very impressive. They can produce very plausible answers, but there can be mistakes, and there is not yet a connection with systems that actually understand, for example, linear algebra or query languages and so on. So there is still work to do in that direction, but this is the direction that in which it is going. And it feels very much like in these science fiction movies, like in Star Trek and the like, where people actually talk to the computer, right? But if that happens, you will still know what's happening behind the scenes with everything that you've learned, and that helps thinking more critically. Then there is this convergence between data, value, money, it's going a bit everywhere, right? So cryptocurrencies is one thing, the fact that you store on some ledger who owns what. This is just an example. It's not an invitation to buy anything. Again, critical thinking, I'm not saying that, but the technology is here. And this is one way that there is a convergence between the notion of data and value. Another way is that you have many products on the internet that are free. And actually, it's not free. It's free because you're not paying with money, but you are actually paying with your data, right? So the data has a lot of value. And fungibility is yet another aspect of that, is that fungible is like electricity, water, this is all fungible, right? You can just let it flow. And the data is also increasingly becoming like this too. Okay. Then there is the data protection problem, because querying data is one thing, knowing how to query data is one thing. But you know, from if you go to the movie theater, that with great power comes great responsibility, right? And if you know how to query all of this data, you can query terabytes or petabytes of data. You need to ask yourself, what is there in the data? Is it data about people that I'm manipulating, right? Did they give their consent to manipulate it, right? So there's plenty of ethical aspects that are not part of this lecture. There are other lectures at ETH. I'm thinking of big data law and policy that teaches that. But whatever you do, you need to be aware of the context, the legal context, and what you need to pay attention to, right? And it's going in a direction in some parts of the world, like in the European Union and Switzerland, of protecting people's right a bit more with respect to data, and especially if you create companies that forces you to consider also these aspects, right? Then there is also some sort of convergence between databases and machine learning or artificial intelligence technologies, not in the sense that we talk to databases, but in a different sense, is that in both ways, actually. Machine learning technologies at the beginning were not really leveraging database technologies. They were just doing their own things before you train the system. But now, with very large scales of data, it's not possible to do it anymore. So you start to build integration between the database technologies and machine learning. For example, you have Spark ML, which is a machine learning framework on top of Spark, and so on. But what's also interesting is that it happens the other way around, that databases might start using machine learning technologies. And this is an example, just so you see the sort of things that's happening. That's at MIT. I told you in the MongoDB lecture that there are two kinds of indices, right? The mostly used indices. What are these? Hash indices and exactly the trees, B plus trees, right? So hashes and trees. Well, it turns out there are people who try something else. This is a machine learning index. Instead of running through your data and storing with hashes and trees, organizing an index like you see at the end of the book, they feed it in a machine learning model. They just feed the data set in a machine learning model, and it just builds, again, some trained model. And at the end, if you want to look up a value in your database, it's not going to look up the hash or how it's in a tree. It's just going to the machine learning model saying, oh, I'm looking for a document about Albert Einstein. And then the machine learning model says, oh, I think it's there, right? But this is all based on machine learning. It's not based on building a hash index or a B plus tree, right? So this is also something that has a lot of potential. Indices is just one aspect of it, but there is ongoing research for many parts of the database, right? And there is now the ongoing jokes in the community of who will eat whom, right? Is it the database, the database community who will eat the machine learning community, or is it the machine learning community who will eat the database community, right? So we'll see the direction in which that all goes. Then there is quantum computing. Quantum computing right now is still a bit of a hype. You probably hear regularly about it in the news. You also see the companies fighting against each other via media posts and so on. So it's actually quite exciting to watch. Who knows a little bit about quantum? Okay, some of you. So the idea of a quantum computer, I simplify, of course, a little bit, right? If you want to know more, you can go visit a quantum computing lecture and so on. It's that you execute computations on different data not in parallel, but as a superposition, right? It's not parallel in the sense that it's on different machine. It's just one machine, the same machine, but it's as if you would do it in parallel world, right? In one world, you're computing that record. In another world, you're computing that record. So it's kind of everything at the same time, right? But of course, there is a constraint, because otherwise it would be too easy. First, at the end of your computations, once you've run the computation at the same time on all of your data, well, you only get one result. You don't get the result, for example, for every record of your database. You only get the result for one single record, for one single value of the input. That's the first limitation. And the second one is you don't even get to choose which one. That's picked randomly for you. You don't get a say, right? So in spite of these two limitations, that you only get one of the results and you don't even get to choose which one, it was still shown that, at least in theory, it outperforms classical computers. And an example of that you might have heard of is the decomposition of numbers into prime factors, right? Which is very hard to do with classical computing. But it turns out that with quantum computers, there is an algorithm that with a high probability is going to give you the prime factors in polynomial time, which is much better than exponential, right? So this is one example of what quantum computers can do better. What we do not know is whether quantum computers can efficiently solve any algorithm. That's called NP. Who heard about NP? Right? These are the very hard problems in computer science that are exponential, the traveling salesman, and so on and so on. We have no idea today if the quantum computers are actually powerful enough for that. In fact, designing quantum algorithms is extremely challenging. It's very, very difficult. We don't know many of them, and it's so complex that not many have managed to develop some. But nevertheless, there is this race towards building bigger and bigger quantum computers, raising the number of qubits, managing to manage the noise, because you can also have a lot of errors in the process that you need to manage. So yeah, very exciting. So this is definitely something to follow about what's going to happen. There are even people who manage to map back the quantum world to relational databases. So if you're interested, there is this paper. So Samson Abramsky is known to in the field of quantum computing. So this is kind of a paper you can read if you are interested in these topics. And then there is the huge long-term thing. It's whether humankind is going to conquer the entire universe, and if we end up just turning all of that into a huge database. But this is more like fun thinking than anything else, right? All right. This is a big thank you to the team. So Wenxi, who is right here. So let's applaud Wenxi, who was courageous to come here. You also have Grigory at the back. Yeah, you can come here if you want. Yeah. Do we have any other TAs? All right. So a big applause also for Grigory when he comes to the front. Yes, applause. Exactly. Okay. So yes, a big thank you to the entire team. So now they are finalizing the exam that we will host in August. And in the meantime, we will help you, of course, prepare for the exam. You also were kind enough to fill in the evaluation forms, which is very important because every time it's an opportunity to improve what we do. So thank you for this. And we are asked by ETH to always communicate the results and discuss the results with you. So quickly, this is what I'm doing here. So here, this is about whether you actually understood what I have been telling you through the entire semester, and it seems you did. So this is always the best, you know, for a teacher, knowing that it made sense and that people understand is the best reward. So I'm really touched by this. Thank you very much. The assistants also did a great job. You see, so ETH basically says 3.5 and above is very good, right? So this is way into the 4 scale. So thank you also for the TA team for doing such a great job. to support you throughout the semester. How did you get along with the material? So one of the questions that I like is whether you're able to explain the material to a younger student, because this is usually how you learn something, you truly learn something and try to explain it to other people. In fact, this is why it's a good idea for the exam when you train to explain to each other what you don't understand. Do not hesitate to interact with each other. That's really the best way to learn. All right, so this is also all in the green. The satisfaction also is very high, so it really means a lot to the whole team. Then there are questions. So here, the goal is to be in the middle, right? So for the first two questions here, so it's about the comparison with other courses in terms of requirements. And here we want to be kind of balanced with the other courses, right? So, and the relationship between credit and time seems to also be under control. And you were inspired by the lecture. So this is great. And then every semester they have fun with us, because when they ask like, in which semester are you, somehow there's a bug in the system and they like to directly give us the data. So that's an exercise for you. You can just feed the data in there and build the SQL group by query and figure out the histogram like this. All right. The exam, we can actually take a break. Maybe I tell you briefly about the exam after the break, but basically just saying everything is part of the exam, right? The slides, the recordings, the textbook, now that that is almost done. Everything that's marked as mandatory reading is basically part of the material. The theoretical and practical exercises, the clicker questions, even though, of course, these are not the same as exam questions because the clicker is to make you think, and so on. All right. I think we can take a break, and right after the break, we'll talk about the exam and have the quiz game, right? So let's take a break and let's meet at 17 past 9. Thank you very much.